In this section, we're going to take a look at functions. Specifically, we want to answer what a function is, how we can determine whether a relation is a function or not, and finally, how we can find the domain and range of a function. Now, if you were to open up your book and say look up the word function, it'd give you some sort of definition like this. If for each value of x there is only one and only one value of y, then the relation is said to be a function. Now, unfortunately, that doesn't really shed a whole lot of light on functions. After all, I can see the definition and maybe decipher a little bit about what it says, but how do I really recognize a function when I come across it? What am I looking for? Well, the problem is that functions are really an abstract concept. So to really delve into this definition, we have to think about another abstract concept so we can make some connections. Instead, we're going to think about this question. What is a bridge? So go ahead and just take a few seconds and get a good picture of a bridge in your mind. Now, you might get a bridge that looks something like this. So notice how I have a nice big steel bridge. It has a road on top. And you'd probably agree that yes, this is an example of a bridge. Unfortunately, it may not match the one you have in your mind. Well, I have another example of one. Your bridge might look something like this. This one's made out of wood. It's a lot smaller and looks like you can only travel over it on foot. But, we'd probably both agree that these are both bridges. Now, even though these are two pretty good examples, it still might not match the one in your mind. Well, the one you have in your mind is probably still a bridge. Well, think about that. Isn't that kind of strange? It doesn't seem to matter what the bridge is made out of. And it doesn't seem to matter whether it's transporting cars or people. Yet it's still a bridge. Well, why is that? Well, the reason why all of these examples are really still bridges has to do what they're intended for. So it's not necessarily what they look like or what they're made out of or their color, but really what they're used for. So we could say that a bridge must connect two different places and that it somehow provides easier movement between the two places. As long as I have something that fulfills that criteria, I can go ahead and call it a bridge. Now, in some way, that's how you want to start thinking of functions. That it may not necessarily matter what they look like or what they're made out of, but it must fulfill this criteria or it must fulfill this definition of a function before we can actually call it a function. Now, here's a quick heads up on some of the notation we use for functions. You may see something like this. This is read, f of x is equal to 3x plus 9, and actually gives us lots of information about the function. The first part of it, that little f, actually just gives us the name of the function. So this function is called f. The part inside parentheses, that does not mean multiply. That's just giving us the name of an input to the function. So the name of the input here is called x. Now on the other side of the equal sign, all of that stuff, that is basically the rule or the relation of the function. It tells us what it does. So this function here, f, what it does with an input is it multiplies it by 3 and then adds 9. Now, what might not be quite clear is why we use this notation in the first place or why we want to learn more about functions. Well, the big idea is that it gives us greater flexibility with expressions and we have much better control over our inputs. So we know a little bit about, say, the criteria that a function must meet, and we also know a little bit about the notation used for functions. But the definition, that criteria, might still be a little hazy. Well, one big idea you want to take from functions is that there's really a notion of inputs and outputs. You see, in some sense, we're going to start treating equations as if they were like little machines. So we can put something into them, and we also get something out. So, schematically, let me show you exactly what's happening. Maybe I have a number like 3, and I can take 3 and put it into this thing called a function. Now, the function has a rule or relation that will take care of that 3 and do different things. When it's all done, it produces some sort of output, like maybe the number 5. Now, you could start taking these inputs and outputs and packaging them up into ordered pairs. So here's the set of inputs and outputs. What this basically says is that when I input a 1, I got an output of a 2. When I used an input of a 3, I got an output of a 5. And you can see I tried 6 and got a 7, put in a 7 and got a 4. So I have inputs and outputs in this function. Now, if you look at those ordered pairs, that is actually an example of a function. And the reason is because it fulfills our criteria. For every value of x in there, it goes to exactly one value of y. Now, if that doesn't look quite clear just yet, let's go ahead and look at this. So I'm basically going to list out my values for x on the left, and then list out my values for y on the right. So on the left, I have 1, 3, 6, and 7, and then on the right, 2, 5, 7, and 4. Now, if you look at the connections between those inputs and outputs, you'll see that for every value of x on the left, it goes to 1 and only one value of y on the right. Therefore, this thing really is a function. Now, if you're still a little bit hazy on that definition of a function, well, I just have one more example that will really hammer it home. And this is basically a story that involves one of my most favorite functions, the Coke machine. So I basically have a very special Coke machine at home that works like this. You walk up to the Coke machine, you press a button, and it gives you the soda you want. Now on the front of my machine, there are basically 3 different buttons. And here's how they work. If you were to go up on that machine and press the red button, it would give you a Coke. If you go ahead and you press the blue button, then it gives you a Pepsi. And finally, if you press that green button, it will give you a Sprite. So as you can see, this Coke machine is really an example of a function. For every input I give it, like that button, red, blue, or green, it will give you one and only one output, either a Coke, Pepsi, or Sprite. So yes, this is a function. See, one of the nice things we like about functions is they have predictability in them. Every time I press that red button, I know I'm going to get Coke. Now, unfortunately, my Coke machine doesn't always work like it should. In fact, I went on vacation for a little bit, and I asked my neighbor Brian to go ahead and watch my house. And when I came back from vacation, my Coke machine started to act very differently. In fact, when I came back, this is what happened. I was very thirsty, and I walked up to my Coke machine and I pressed that red button. Unfortunately, this time I didn't get a Coke. No, this time it actually spit out a Pepsi. But I was really thirsting for a Coke. So you know what? I went ahead and I tried to press that red button one more time. Only this time, it actually gave me a Sprite. Now, I thought that was really strange. It's never done this before. So I pressed that red button again, and it gave me another Sprite. It seemed like I couldn't really predict what was coming out of this Coke machine anymore. So I pressed that red button one more time, and finally it gave me a Coke. Well, I marched over to my neighbor's house, and I said, "Hey, what's going on here?" And it turns out he was playing a little bit of a trick on me. He went through my Coke machine, and he mixed up all of my cans. Well, as you can see, I now give it one input, say that red button, and I get 3 different outputs. Well, because of this, my Coke machine is no longer a function. Now, fortunately, I was able to get my Coke machine back into working order, and so everything started to work like normal. Or at least, it did for a little while. One day I went up to my machine, and it again started to act very strange. Only this time, when I went up and I actually pressed that red button, it gave me something completely different. It gave me a Pepsi. I thought, okay, well, that's really strange. And I pressed the red button again, and it still gave me a Pepsi. Well, I went over to my neighbor and asked him if he had been messing with my cans again, and it turned out he had not touched the machine. So I went back to my Coke machine, and this time I pressed the blue button. And lo and behold, it gave me another Pepsi. Well, I really want a Coke. And I only have one button left on the machine, so I went ahead and I pressed that one as well. And what do you know? It also gave me a Pepsi. Now, even though this looks like a similar situation, it's actually completely different. Notice how that no matter what input I give it, I keep getting the same output. In this situation, it turns out that my wife, she came across a great sale on Pepsi, and she decided to stock my machine with nothing but Pepsi. The big question is this really a function or not, though? It turns out that this is a function. The reason is, every time we put in an input, say red, we get exactly one output, Pepsi. And it just happens in this case that all of the outputs are the same, still Pepsi. So yes, this is a function because it fulfills the criteria. So hopefully that makes it a little bit more clear how you can recognize a function or not. Remember that just looking at what represents a function isn't quite enough, because sometimes you can use equations, graphs, or even ordered pairs to represent these different functions. The true test is to see whether it satisfies the concept or the definition of a function. So every input I give it, does it go to 1 and exactly 1 output? On to a quick concept check. So when looking at the following relation, is it a function or not? Remember to think about the definition of a function to really give it the true test. It turns out that this is not a function. The reason has to do with the number 1. Notice how 1 is the input and it has two different outputs. It goes to 4 and it goes to 0. That's a problem. That means every input doesn't necessarily go to one output. So that is definitely not a function. Now look at this example. Here I have a set of ordered pairs which represent inputs and outputs. Would you say this is a function? If you said yes, then you're definitely on the right track. Every input here goes to exactly one output. So it is a function. Now on to some quick terms. The domain of a function is the set of all the inputs, and the range of a function is the set of all the outputs. So if I was to grab, say, a quick example of inputs and outputs, let's see what I mean. So here my inputs are 1, 3, 4, 7, and my outputs are 3, -2, 5, and 10. So if I collect together all of those inputs, I can call them the domain. And if I collect together all of those outputs, I can call them the range. Now, if all functions were represented using a set of ordered pairs or even a diagram, it would be an easy task trying to figure out what is in the domain and what's in the range. But remember that sometimes we can use equations to express these different functions. In order to determine the domain and range when it's expressed in that way, look for problem areas in the equation. For example, if there's a fraction in the equation, check the bottom to see if it ever becomes a 0. The reason why that would cause a problem is because we can't divide by 0. So if any values make the bottom 0, take them out of your domain. When it comes to, say, even roots, like a square root or even a fourth root, then we want to make sure that underneath the root it stays positive. So we want to eliminate any numbers that would make it negative underneath. So let me show you a quick example of what I'm talking about. Here I have written a function and I'm using an equation to basically do that. Now first I'm going to assume that all real numbers will work in my domain. But when I start to examine it a little bit closer, I notice that it has basically a giant fraction in it. So I start to worry about where the bottom might equal 0. Well, if you look at just the bottom of this fraction, you can see that if you start using different values like x equals -1, that would create a problem. When you use x equals -1, you have -1 plus 1, and therefore you get a 0 in the bottom. Well, since we can't divide by 0, I want to remove that -1 from the rest of my numbers. So basically, my domain would include all real numbers, except for that -1. So here's one way that I can express it. This is known as interval notation, and it basically gives me a range of values that would work in my domain. The way it works is I have two endpoints for this interval notation. So all the numbers between -infinity and -1 would work in my domain. That little u means or, so I could also use numbers in the other interval, between -1 and infinity. Collectively, what this says is that my domain includes all real numbers, just not -1. And remember, that again comes from where the bottom would equal 0. Here's one more quick example. In this one, I have that f of x equals the square root of x plus 5. Again, I start by assuming that in my domain I'll have all real numbers. And then upon closer inspection, I can see that this has an even root. And so I want to make sure that underneath the root, it always stays positive. Well, one problem that I might have is if I start using numbers, say, like -7 or -8. Using numbers like that, I would have a negative number underneath my root. If I use a -5, that actually seems to be okay, because -5 plus 5 would give me a 0, and it is okay to take the square root of 0. You just get 0. Now if I move anything above -5, say at -4 or -3 or -2, those are good as well, because I'd again end up with some sort of positive number underneath the root. So the way I would describe this domain is I would say that I could include all numbers between -5 all the way up to infinity. And notice in this one, I'm using a square bracket because it is okay to include the -5. Again, first start off by assuming all real numbers will work, and then look at what you can eliminate from the domain.